Now, let's welcome our first speaker, Mr. Philip Anggo Krisbiantoro from Indonesia. He is presently a third-year PhD candidate in the TIGP Molecular Science and Technology program. His research focuses on heterogeneous catalysis, plastic upcycling, and MOF synthesis under the guidance of Dr. Chia-Wen Wu from National Taiwan University.
Okay, so thank you very much, Chair, for the kind introduction, and it is an honor for me to share one of my works in this occasion. So today I would like to highlight that ways PET-derived PHT can be used for rapid solvent-free MOF synthesis. As we know that the global plastic production is rapidly increased over the years, and it has reached 370 million tons in 2020. Unfortunately, the majority of them, which is around 80%, has become landfill pollutants. And of course, that pollution with plastic is having negative impact, not only to environment, but also human health. And it is indeed that the only way to reduce global plastic production and pollution is just by recycling, either by physical or chemical recycling, and energy recovery by incineration and pyrolysis. And among these three techniques, chemical recycling is the most effective and efficient technique for recycling because it can convert plastic into the smallest fragments that can be used for the synthesis of so many kinds of high value added chemicals. And there are two commonly used techniques for chemical recycling, hydrolysis and glycolysis. In the case of hydrolysis, the final product is terephthalic acid, or so-called S2-PDC. Meanwhile, in the case of glycolysis, the final product is bis-2-hydroxyacyl terephthalate, or so-called PHT. So the next question is, what is the application of these two compounds? In industry, these two compounds are the main component for the synthesis of so many kinds of polymers. And although, of course, that these polymers products are highly useful for our daily life, but maybe we can use S2-PDC and PHT for the synthesis of other products that have more value than these polymer products. For example, we can use S2-PDC and PHT for MOF synthesis because, of course, that MOFs are very important material that actually define our 21st century. And by using S2-PDC and PHT for MOF synthesis, we actually combine two of the top 10 emerging technologies in chemistry by IUPAC, which is MOF number 6 and plastic to monomers number 8. And the idea of using PET monomer for MOF synthesis, especially PDC-based MOF, have been reported before. And all of these reports, they follow this pathway. So they firstly hydrolyze PET to produce S2-PDC, and then they use the as-produced S2-PDC for the synthesis of PDC-based MOF by using solvent approach. And although, of course, that this technique or this pathway is already very, very good, however, it has some major drawbacks. For instance, PET hydrolysis is a reaction that requires harsh conditions. And MOF synthesis by using solvent approach is actually simply not green because it uses large amount of organic solvents. And therefore, what if instead we using this pathway, we develop our own pathway? For example, we can change hydrolysis with glycolysis because, of course, the reaction conditions for PET glycolysis are much milder than that of PET hydrolysis. And we can change solvent approach for MOF synthesis by using solvent-free approach because, of course, it is much easier to handle and more green as compared to that of solvent approach. And the most important thing about this pathway is that this has not been reported yet so far. And therefore, the objective of my work is that I simply want to use PHT that I produce from PET glycolysis reactions from my previous work in this journal for the synthesis of metal organic frameworks by using solvent-free grind and bake technique. And the MOF that I want to demonstrate here is UaO66 zirconium. So how to get this material? It's very easy. In typical synthesis, 1.5 millimole zirconium precursor and 1.5 millimole PHT were grind for 15 minutes and then transfer into an autoclave, bake at 130 degrees C for 12 hours, and then wash with ethanol 3 times, and finally freeze dry overnight to get the material. And then next, we move to the result and discussion. And this is the screening of zirconium precursor. As we can see here from XRD spectra, out of 4 different types of zirconium salts, only zirconium tetrachloride and zirconyl chloride octahydrate can give the XRD pattern of UiO66 under the synthesis conditions. And let's denote the material as UiO66 zirconium tetrachloride and UiO66 zirconyl chloride. And these first results further confirm that for the first time, PHCT is used as a linker source for the synthesis of PDC-based metal organic frameworks. And to further confirm that the synthesized material was really UiO66, I characterized the material by using several types of characterizations, including XRD, SEM, TGA, PET, FTIR, and Raman spectra. And as we can see here, all of these characterization results are typical results from the UiO66 and very similar to the paper that firstly reported UiO66 in this journal. And the most important take-home message for everybody here from this finding is that, yes, for the first time, PHCT is used as a linker source for the synthesis of metal organic frameworks, especially UiO66. However, the most important question in this work is that how to elucidate the reaction mechanism, how PHCT was converted into PDC to form UiO66. To answer these questions, we need to firstly understand what happened during the grinding, and then next, what happened during the baking. First, let's try to understand what happened during the grinding. So to understand what happened during the grinding, I grind zirconium precursor and PHCT for 15 minutes and then characterize the results simply by using XRD. And as we can see here, after 15 minutes of manual grinding, we can observe 111 and 200 planes which actually belong to the cluster of UiO66. However, when I try to wash the product by using ethanol, both of them were dissolved. What does it mean? This means that while the clustering process already started, the stable crystal of UiO66 was not formed yet at this stage. And let's call the product as pre-UiO66 zirconium. To further understand what happened to zirconium precursor during manual grinding, I grind zirconium precursor for 15 minutes without PHCT and then characterize the results by using XRD. And in the case of zirconium tetrachloride, I found that during manual grinding, it indirectly converted into zirconium cluster through the formation of zirconyl chloride hydrate. And this species was formed by the hydrolysis of zirconium tetrachloride by the moisture. And this is supported by the fact that the weight after grinding was always higher than the weight before grinding. Meanwhile, in the case of zirconyl chloride octahydrate, it can be directly converted into zirconium cluster. The next question is how zirconium cluster was converted into, how zirconium precursor was converted into zirconium cluster. To answer these questions, we need to firstly remember that zirconium tetrachloride is highly hygroscopic and therefore subject to hydrolysis under air. And although it is reported that these reactions is endothermic, however, the grinding process may give the required energy for the hydrolysis. Again, this is supported by the fact that the weight after grinding was always higher than the weight before grinding, indicates the absorption of moisture. Meanwhile, in the case of zirconyl chloride octahydrate, it can be easily converted into zirconium cluster because this reaction is simply highly exothermic. And from the FTIR analysis, I found that during manual grinding, PHCT was interacted with zirconium cluster simply through carbonyl hydrogen bond and ether hydrogen bond. So what we know so far from 15 minutes of manual grinding is that first, zirconium cluster was formed, and second, PHCT interacted with zirconium cluster simply through hydrogen bond. And next, let's try to understand what happened during the baking. So to answer these questions, I did some literature survey, and it is widely reported that the hydroxyl ends of the amphoteric metal oxides are actually capable of hydrolysing ether to form interfacial carboxylates that bind with the metal oxide. And this is very similar with my works. Why? Because of course, then the zirconium cluster in my work is highly hydroxylated as the result of the hydrolysis of zirconium precursor. And moreover, the amphoteric nature of the hydroxylated zirconium cluster make it easier to be protonated by chloric acid produced from the clustering process of zirconium precursor. And therefore, it is proposed that in the baking process, PHCT was protonated by the surface proton from the zirconium cluster followed by hydrolysis, dehydration, and coordination to form UF66 crystal. And this proposed mechanism was supported by the fact that ethylene glycol, which is the side product of these reactions, was detected in the washing filtrate. And then after I elucidated the reaction mechanism, I did the effect of baking temperature and time. And at baking time 12 hours, I found that we can actually decrease the baking temperature to just 70 degrees without significant decrease in the product yield. Meanwhile, from the effect of baking time, at 130 degrees C, we can decrease the baking time to just 30 minutes, allow the rapid synthesis of the material. And then this is the comparison with other works. As we can see here, the synthesis conditions in these works are much milder than any previously reported sulfur thermal technique and any previously reported grind and bake technique. And the fact that I can get other PDC-based MOF, I apologize, by using PHCT as linker source suggests that PHCT is a feasible linker source for the synthesis of other PDC-based MOF, including UF66 hafnium, copper PDC, and MIL53. And in conclusions, these works demonstrate the easiest way to synthesize PDC-based metal organic frameworks. Thank you very much for your kind attention.